Welcome to tonight's journey into the deep ocean. Close your eyes and let your breathing slow down. The world above the surface is finally quiet. Leave the stress of your daily life behind. Tonight we travel far beneath the rolling waves. We are sinking into a realm of absolute peace. Your mind can rest in this tranquil aquatic space. The ocean offers a perfect sanctuary for deep sleep. Our destination lies in the vast Pacific Ocean. We are heading toward the Juan de Fuca Ridge. This submarine mountain range remains hidden from human eyes. It is the most extensively studied hydrothermal vent system. Scientists have spent decades mapping this underwater landscape. We will explore its mysteries at a gentle pace. You are completely safe on this virtual deep dive. Let the rhythmic motion of the water soothe you. We begin our descent through the twilight zone. The surface light slowly fades into a calming dusk. Our submersible glides smoothly through the cooling water column. The pressure inside our vessel remains perfectly comfortable. The Juan de Fuca Ridge sits off the coast. It parallels the shores of Washington and British Columbia. We navigate towards specific coordinates in the Northeast Pacific. Our instruments lock onto 46 degrees north latitude. The longitude reads 130 degrees west. This precise location marks a significant geological boundary. We are roughly 300 miles from the mainland. The coastal shelf drops away far behind us now. Open ocean stretches endlessly in every single direction. Surface weather patterns have no effect down here. The water temperature steadily drops as we go deeper. We pass the 1,000-meter mark with ease. Sunlight cannot penetrate beyond this specific ocean depth. We have entered the midnight zone of the sea. Absolute darkness wraps around our descending research vessel. This pure darkness is peaceful rather than intimidating. It provides a blank canvas for your resting mind. Oceanographer John Delaney spent years studying these exact coordinates. His research helped define this unique underwater geography. The ridge spans over 300 miles in length. It forms a rugged spine along the ocean floor. This location is isolated from all terrestrial interference. Only specialized acoustic equipment can map these remote coordinates. The sonar pings reveal a complex topography below us. The Juan de Fuca Ridge is a divergent boundary. Here two massive tectonic plates are slowly moving apart. The Pacific Plate drifts steadily toward the west. The smaller Juan de Fuca Plate moves eastward. They separate at a rate of 6 centimeters annually. This gradual spreading creates a gap in the crust. Molten rock rises from the mantle to fill it. This continuous process forms fresh ocean floor every day. Geologist William Chadwick has monitored this spreading center extensively. His instruments record the subtle shifts in the crust. The tectonic forces operate in extreme slow motion. You can imagine the Earth breathing at this boundary. The slow expansion releases heat from the planetary interior. This heat interacts with the freezing seawater above it. The Juan de Fuca Plate is also sinking eastward. It slides beneath the massive North American Plate. This subduction zone creates the nearby Cascade Mountain Range. But our focus remains on the spreading ridge itself. The ridge axis features a deep central rift valley. This valley is flanked by parallel volcanic mountain ridges. The tectonic activity here is silent to human ears. Low-frequency sensors detect the deep geological rumblings. These vibrations are a natural lullaby of the Earth. The crust here is remarkably thin and highly fractured. Seawater seeps down through these deep basaltic faults. It travels miles beneath the heavy ocean floor. The water approaches the shallow magma chamber below. This sets the stage for complex hydrothermal circulation. The tectonic setting makes this area scientifically invaluable. Researchers use it as a natural laboratory for geophysics. Every square meter holds clues to planetary evolution. The spreading center is a cradle of geological creation. It operates in the quiet solitude of the abyss. Our submersible finally approaches the rugged sea floor. The depth gauge reads exactly 2,200 meters. Some sections of the ridge dip to 2,500 meters. At this extreme depth, the environment transforms completely. The ambient water temperature hovers near 2 degrees Celsius. This near-freezing cold is constant and unchanging. The hydrostatic pressure here is truly incredibly immense. It measures roughly 250 atmospheres. This equals nearly 3,700 pounds per square inch. Every surface of our vessel bears this heavy weight. The thick titanium sphere protects us from the crushing force. You can feel safe within this engineered metal sanctuary. The pressure alters the fundamental properties of the seawater. Gases dissolve much more readily into the surrounding liquid. Water density increases slightly under this massive physical burden. This heavy blanket of water insulates the ocean floor. It shields the ridge from all surface weather events. Storms and hurricanes above cannot reach this deep sanctuary. The deep ocean remains perfectly still and profoundly silent. The immense pressure prevents seawater from boiling easily. Even at high temperatures, the liquid remains entirely stable. This physical reality allows for unique chemical reactions. Scientists carefully calibrate their instruments for these extreme conditions. Specialized robotic vehicles navigate the crushing pressure with ease. They transmit data back to the surface via fiber optics. The depth creates a natural barrier to human intrusion. Only the most dedicated researchers ever visit this realm. The journey down takes several hours of patient waiting. This slow descent mirrors the process of falling asleep. You sink deeper into relaxation with every passing meter. The weight of the water above is strangely comforting. It acts like a heavy blanket over the world. Your mind can drift freely in this pressurized space. The eternal darkness of the deep ocean is absolute. No stray photons from the sun can reach us. The water absorbs all visible light near the surface. This creates a permanent and unending midnight environment. Our submersible turns on its powerful exterior LED lights. The bright beams cut through the pitch-black water. They reveal the surrounding terrain of the Juan de Fuca Ridge. We are flying over a vast plain of volcanic basalt. The seafloor is paved with dark glassy rock formations. Massive pillow lavas dominate the immediate underwater landscape. These bulbous shapes formed when hot magma met cold water. The rapid quenching created smooth and rounded rocky mounds. Some formations look like giant tubes of dark toothpaste. Others resemble piles of smooth black river stones. A fine layer of pelagic sediment covers the older rocks. This marine snow falls constantly from the waters above. It softens the harsh edges of the volcanic terrain. The newer lava flows remain sharp and completely bare. We glide over deep fissures cracking the ocean floor. These narrow canyons stretch for miles along the ridge. Small seamounts rise gently in the peripheral distance. They are dormant volcanoes from past geological eras. The terrain is a mosaic of destruction and creation. Collapsed lava tubes form shallow depressions in the crust. Sheet flows create flat expanses of smooth dark rock. The headlights cast long eerie shadows across the basalt. The landscape looks remarkably like the surface of the moon. It is barren and alien yet undeniably beautiful. The quiet majesty of this terrain commands deep respect. We hover silently above a particularly large lava pillar. The water is crystal clear and free of turbulence. You can observe every detail of the rocky structures. This peaceful exploration requires no physical effort from you. Simply let the imagery float through your resting mind. The deep sea offers an escape from the ordinary. There are no rushing winds or loud city noises. Only the gentle hum of our submersible thrusters remains. We navigate carefully around a towering basaltic chimney. These geological features take thousands of years to build. Minerals precipitate very slowly from the surrounding cold seawater. The Juan de Fuca Ridge is a geological marvel. Scientists consider it a window into the inner earth. The lack of sunlight means no plants can grow here. Yet the rocks themselves seem to possess a quiet life. The shifting tectonic plates ensure constant slow transformation. Every crack in the basalt tells a story of heat. The deep ocean pressure preserves these formations perfectly. Currents move sluggishly across the uneven volcanic plains. They carry microscopic particles through the vast dark expanse. The water acts as a dense medium for sound transmission. Acoustic signals travel vast distances in this pressurized realm. Researchers use sound waves to map the hidden valleys. The resulting charts reveal a highly complex fracture zone. We are exploring a world entirely defined by geology. The intersection of fire and water happens continuously here. Magma from the mantle provides the ultimate heat source. It drives the entire physical system of the ridge. The cold ocean acts as a massive thermal sink. This extreme contrast creates a perfectly balanced natural engine. The Juan de Fuca Ridge never truly sleeps or rests. But its endless geological work is completely silent. You can safely observe this immense power from afar. The darkness outside our viewport is incredibly soothing. It invites you to release all lingering mental tension. The heavy pressure of the deep sea embraces you. It holds you securely in a state of profound calm. Our journey along the ridge has only just begun. The landscape stretches endlessly into the black waters ahead. We will continue to map this fascinating underwater world. Rest your mind as we glide over the ancient rocks. The geological history of the Earth is written here. Every lava flow represents a moment of planetary creation. The deep ocean keeps these historical records perfectly safe. No human footprints will ever disturb this volcanic dust. The Juan de Fuca Ridge remains a pristine scientific sanctuary. We respect the quiet isolation of this profound environment. The steady temperature and pressure provide deep environmental stability. This stability allows unique geochemical processes to occur naturally. You are witnessing the raw architecture of our planet. The ocean floor continues to spread in the darkness. Let the vastness of the Pacific Ocean calm your thoughts. The miles of water above protect this hidden realm. You are completely insulated from the frantic surface world. Breathe slowly as we drift above the silent basalts. The deep sea is the ultimate place for relaxation. Our exploration of the ridge will slowly unfold tonight. There is no need to rush our careful observations. The mysteries of the ocean floor will reveal themselves. Embrace the peaceful solitude of the deep Juan de Fuca. Sleep will come very easily in this vast dark aquatic sanctuary. The deep water outside remains perfectly still and deeply cold tonight. Let the heavy ocean wrap you in total peaceful tranquility now. The story of this deep-sea ridge begins with faint clues. Oceanographers long suspected hidden activity off the Pacific Northwest coast. Early depth soundings revealed a massive underwater mountain range. This geological structure sits roughly 300 miles offshore. Scientists noted unusual magnetic patterns across the ocean floor. These magnetic stripes suggested active seaflow spreading in the region. The Juan de Fuca plate was actively separating from the Pacific plate. Water above the ridge showed slight temperature variations. These thermal anomalies puzzled researchers in the late 1970s. Something beneath the crust was heating the deep ocean water. The famous Galapagos Rift discovery occurred in 1977. That monumental finding proved the existence of deep ocean hydrothermal vents. Scientists immediately began searching for similar vent systems elsewhere. The Juan de Fuca Ridge became a prime target for exploration. Its proximity to the North American continent offered a distinct logistical advantage. Research vessels could reach the coordinates within a few days of sailing. The United States Geological Survey organized preliminary surveys of the area. They focused their attention on the southern segment of the ridge. Deep tow cameras were prepared for the long descent into darkness. These early camera sleds were towed miles behind the surface ships. In 1981, a dedicated expedition finally launched. The research vessel Thomas G. Thompson sailed from Seattle. Geologist William Normark led the team of eager oceanographers. John Delaney from the University of Washington joined the ambitious project. They targeted a specific area known as the Endeavour segment. The ship reached the designated coordinates at 47 degrees north. The ocean depth here measured roughly 2,200 meters. A heavy camera sled was lowered slowly through the water column. Steel cables unspooled for hours as the equipment sank downward. The sled hovered just meters above the rugged basaltic seafloor. Strobe lights illuminated the perpetual darkness of the abyssal plain. The camera captured thousands of black and white photographs. Researchers anxiously developed the film in the shipboard darkroom. The resulting images revealed something entirely unprecedented for this region. Massive mineral chimneys rose like ancient ruins from the rock. Dark plumes of mineral-rich fluid billowed from the chimney tops. This was the first visual confirmation of black smokers on this ridge. The scientific community received the news with quiet but profound interest. The Juan de Fuca Ridge hosted a massive hydrothermal system. These vents were far larger than those found at the Galapagos Rift. Photographic evidence alone could not satisfy the scientific curiosity. Researchers needed physical samples of the vents and the surrounding biology. The deep submergence vehicle Alvin was called to the Pacific Northwest. This famous titanium submarine was operated by the Woods Hole Oceanographic Institution. The research vessel Atlantis II served as Alvin's dedicated mothership. Engineers spent months preparing the submersible for the cold northern waters. The expedition was scheduled for the late summer of 1984. Weather conditions in the Northeast Pacific are notoriously unpredictable. The team needed a narrow window of calm surface waters. Launching and recovering the heavy submarine requires relatively flat seas. The morning of the first dive was shrouded in dense coastal fog. 3 crew members climbed into the cramped titanium sphere. The heavy hatch was sealed tight against the immense ocean pressure. Alvin was lowered gently into the frigid dark blue water. The submersible began its slow descent toward the ocean floor. Sunlight faded completely within the first 1,000 meters of depth. The pilots relied entirely on sonar instruments to navigate the darkness. The descent to the ridge axis took over 2 hours. The internal temperature of the sphere dropped steadily during the plunge. Condensation formed on the thick acrylic viewports of the submarine. External pressure reached 220 atmospheres at the bottom. The pilot switched on the powerful exterior metal halide lights. A barren landscape of fresh pillow lava appeared outside the windows. The submarine drifted slowly over the jagged volcanic terrain. They were searching for the exact coordinates of the camera sled photographs. Water temperature sensors mounted on the submarine showed a sudden increase. The ambient deep ocean water is normally around 2 degrees Celsius. The digital thermometers suddenly registered temperatures above 10 degrees. This thermal gradient indicated they were approaching an active vent field. The water grew cloudy with suspended particulate matter. A towering structure suddenly loomed in the narrow beam of light. It was a massive sulfide chimney standing 15 meters tall. Thick black smoke poured violently from the top of the spire. The pilots carefully maneuvered Alvin closer to the raging thermal vent. They deployed a specialized titanium temperature probe into the dark plume. The digital readout inside the sphere climbed at an astonishing rate. The vent fluid temperature measured exactly 350 degrees Celsius. The intense pressure kept the boiling water in a liquid state. This superheated fluid was completely devoid of any dissolved oxygen. It carried massive concentrations of dissolved iron, sulfur, and zinc. The scientists noticed dense clusters of life surrounding the chimney base. Thick thickets of tube worms clung to the mineral deposits. These organisms were entirely different from the Galapagos species. Biologists later identified them as a unique species called Ridgeopisces. They possessed bright red plumes extending from slender white tubes. These worms thrived in the steep chemical and thermal gradients. Spider crabs crawled slowly among the tangled masses of tube worms. Eelpout swam lazily through the shimmering warm water near the vents. The sheer volume of biomass in this dark environment was staggering. This ecosystem relied entirely on chemosynthesis rather than solar energy. The pilot used the hydraulic manipulator arms with extreme precision. They carefully broke off a small piece of the active chimney structure. The mineral sample was secured in the exterior payload basket. Specialized syringes were used to capture pristine samples of the vent fluid. These water samples were sealed tightly to prevent contamination during ascent. The researchers spent for hours exploring the immediate vicinity of the vent. They mapped the spatial distribution of the surrounding biological communities. Every observation was recorded meticulously on audio cassette tapes. The submarine batteries eventually signaled the need to return to the surface. Iron weights were dropped to restore positive buoyancy to the vessel. The journey back to the surface was a quiet period of reflection. The scientists reviewed their notes and prepared for the laboratory work. Alvin broke the ocean surface late in the afternoon. Swimmers quickly attached recovery lines to the bobbing white submarine. The massive crane hoisted the vehicle back onto the ship deck. Researchers immediately rushed to secure the precious geological and biological samples. The vent fluid samples smelled strongly of hydrogen sulfide gas. The mineral fragments glittered with deposits of fool's gold and sphalerite. These physical samples confirmed the immense chemical output of the ridge. The Juan de Fuca Ridge was acting as a massive chemical reactor. The success of the initial dive sparked a wave of new expeditions. Oceanographers realized the Juan de Fuca Ridge was incredibly diverse. Different segments of the ridge exhibited entirely different geological characteristics. The axial seamount was discovered further south along the ridge line. This massive underwater volcano featured a large central caldera. Scientists found extensive hydrothermal venting within this collapsed volcanic crater. The National Oceanic and Atmospheric Administration established a dedicated research program. The VENTS program was created specifically to study this unique region. Alexander Malahoff led numerous mapping expeditions using advanced multibeam sonar. High-resolution bathymetric maps revealed the complex topography of the entire ridge. Another major discovery occurred at the Explorer Ridge segment. Researchers located a massive sulfide deposit known as Magic Mountain. This area contained dozens of active and extinct hydrothermal chimneys. The mineral deposits here were estimated to weigh hundreds of thousands of tons. These findings highlighted the economic potential of deep-sea minerals. However, the primary focus remained firmly on pure scientific understanding. Scientists wanted to understand how these vents influence global ocean chemistry. The continuous flow of minerals alters the composition of seawater over time. The ridge provides a steady supply of iron to the Pacific Ocean. This iron acts as a crucial nutrient for microscopic surface algae. Early expeditions relied entirely on brief visits by manned submersibles. Scientists recognized the severe limitations of this observational method. They were only seeing tiny snapshots of a highly dynamic system. The vents were prone to sudden changes from seismic activity. Earthquakes frequently rocked the ridge as tectonic plates shifted. These volcanic events could create new vents or destroy existing ones. Researchers dreamed of establishing a permanent presence on the ocean floor. The Juan de Fuca Ridge was the perfect candidate for this ambitious idea. Its relatively short distance from the coastline made cable connections possible. This proximity would eventually lead to the world's first cabled ocean observatory. The late 1980s brought new technological tools to the ridge. Remotely operated vehicles began replacing manned submersibles for routine surveys. The ROV Jason was deployed to map the vent fields in high definition. These robotic vehicles could remain submerged for days at a time. They sent live video feeds up a fiber optic tether to the ship. Scientists could now watch the deep-sea environment from comfortable control rooms. This technological shift dramatically increased the volume of collected data. Time-lapse cameras were left on the seafloor to monitor tubeworm growth. Temperature loggers recorded the continuous fluctuations of the vent fluids. Acoustic sensors listened for the faint rumblings of underwater earthquakes. Every new expedition to the ridge revealed unexpected complexities. Geologists studied the exact chemical composition of the basaltic crust. They measured the precise rate of seafloor spreading at 6 centimeters annually. This intermediate spreading rate creates unique fault structures along the Rift Valley. Biologists discovered microscopic archaea living deep within the rock crust. These extremophiles survive at temperatures previously thought impossible for life. The discovery of the subsurface biosphere fundamentally changed biological sciences. The Juan de Fuca Ridge became the global standard for vent research. More scientific papers have been published about this ridge than any other. It serves as a natural laboratory for understanding planetary processes. The early days of exploration were marked by continuous astonishment. Each dive brought entirely new species and geological formations to light. The pioneering scientists mapped a dark world of extreme conditions. Their foundational work paved the way for modern oceanographic studies. The maps they drew are still used by underwater vehicles today. The physical samples they collected remain preserved in global archives. The story of discovery here is a testament to human curiosity. It required immense engineering skill to reach these hostile depths. The collaboration between geologists, biologists, and engineers was truly unprecedented. The Juan de Fuca Ridge had finally yielded its deepest secrets. These early discoveries forever changed our understanding of the ocean. The Juan de Fuca Ridge represents a dynamic tectonic boundary. It sits quietly off the northwestern coast of North America. Here, two massive pieces of the Earth crust slowly separate. The Pacific Plate drifts steadily toward the vast western horizon. Meanwhile, the Juan de Fuca Plate moves eastward toward land. This divergent boundary creates a continuous underwater volcanic mountain range. Deep beneath the ocean's surface, geological forces shape the planet. The volcanic ridge axis lies approximately 300 miles offshore. Average depths reach 2,200 meters down here. Water pressure at this extreme depth exceeds 200 atmospheres. This modern ridge is a remnant of the Farallon Plate. Millions of years ago, the Farallon Plate covered this ocean. It gradually subducted beneath the advancing North American continental landmass. The Juan de Fuca Plate is a small surviving fragment. Its crustal age near the spreading center is incredibly young. Fresh rocks emerge continuously from the dark, freezing ocean floor. Further away from the axis, the basaltic crust grows older. Sediment slowly buries the ancient rocks over millions of years. Scientists use radiometric dating to measure these vast geological timespans. Isotopes of argon and potassium reveal precise ages of rocks. The Juan de Fuca Ridge is an intermediate spreading center. It separates at a rate of 6 centimeters per year. This movement roughly equals the growth rate of human fingernails. It moves faster than the slow-spreading Mid-Atlantic Ridge. However, it spreads slower than the rapid East Pacific rise. This intermediate speed creates a distinct and rugged structural morphology. A central rift valley runs along the entire ridge axis. The valley floor drops several hundred meters below the peaks. Steep fault scarps form the walls of this axial valley. Tectonic tension stretches the brittle crust until it finally breaks. A persistent magma chamber lies 3 kilometers beneath the seafloor. Decompression melting of the upper mantle feeds this liquid reservoir. Superheated rock rises slowly from the deep, viscous asthenosphere layer. As pressure decreases, the solid mantle partially melts into basalt. This molten magma collects in a thin, lens-shaped chamber. Periodic tectonic shifts force the magma upward through narrow dikes. These vertical conduits transport liquid rock to the ocean floor. When magma erupts underwater, it encounters near-freezing abyssal seawater. The ambient oceanic water temperature hovers around 2 degrees Celsius. This extreme temperature difference causes rapid cooling of the lava. Molten rock extrudes slowly to form bulbous, rounded pillow lavas. A glassy crust forms instantly on the hot lava surface. Pressure builds inside the pillow until the brittle crust breaks. A new lobe of lava squeezes out into the darkness. These overlapping basalt pillows cover vast areas of the seafloor. During higher effusion rates, flat sheet flows dominate the landscape. Liquid basalt spreads rapidly across the flat axial valley floor. Lobate lavas form hollow crusts over flowing subterranean lava tubes. When the lava drains away, the fragile crusts often collapse. Submersible Alvin frequently navigates through these jagged, sunken collapse pits. Mid-ocean ridge basalt forms the uppermost layer of crust. This dark volcanic rock contains high levels of heavy magnesium. Iron and calcium silicates dominate the dense basaltic mineral composition. Beneath the lava layer lies a complex zone of dikes. These parallel dikes represent old pathways of ancient magma eruptions. Deeper still, the crust consists of massive, solid gabbro formations. Gabbro crystallizes slowly within the insulated, warm subterranean magma chamber. Below the gabbro lies the Mohorovicic discontinuity, known as Moho. This fundamental boundary separates the oceanic crust from the mantle. Dense peridotite rock makes up the underlying upper mantle layer. The cooling oceanic crust contracts and cracks over passing centuries. Deep fissures open in the newly formed, brittle basaltic rock. Cold seawater slowly percolates downward through these porous fault lines. The water descends several kilometers toward the hot magma chamber. Extreme pressure prevents the descending water from boiling into steam. Temperatures eventually exceed 400 degrees Celsius in the depths. This superheated fluid becomes highly buoyant and extremely chemically corrosive. A complex chemical exchange begins between the water and rock. The modified seawater strips heavy metals from the surrounding basalt. Magnesium drops out of the fluid entirely during this process. The acidic fluid dissolves iron, copper, and zinc from rocks. Silica and calcium also enter the rising, heated hydrothermal solution. Sulfur from the basalt converts into dissolved hydrogen sulfide gas. This mineral-rich fluid rapidly ascends back toward the ocean. It travels upward through highly permeable, fractured vertical fault zones. The fluid finally exits the crust through focused hydrothermal vents. Upon hitting the cold ocean, the dissolved minerals instantly precipitate. Microscopic particles of metallic sulfides cloud the dark abyssal water. This phenomenon creates the famous, billowing black smoke event plumes. The particles slowly settle to build massive, towering sulfide chimneys. Anhydrite forms the initial structural framework of every new chimney. This calcium sulfate mineral only precipitates at very high temperatures. As the anhydrite matrix grows, it insulates the rising fluid. Inside the porous walls, chalcopyrite begins to crystallize very rapidly. Chalcopyrite is a golden mineral composed of copper and iron. Sphalerite, a dark zinc sulfide, forms in the cooler margins. Pyrite, or fool's gold, reinforces the thick exterior chimney walls. Silica slowly fills the remaining microscopic voids in the structure. White barite crystals often decorate the outer surfaces of vents. Over decades, these mineral deposits grow into towering underwater spires. Axial seamount is the most prominent geological feature found here. Coordinates mark 46 degrees north, 130 degrees west. This massive underwater volcano rises 700 meters in height. It forms where the Juan de Fuca Ridge intersects hotspots. The Cobb hotspot provides an additional source of deep magma. A large rectangular caldera defines the summit of axial seamount. This caldera measures 3 kilometers wide and 8 kilometers long. The caldera floor lies 1,500 meters below the surface. Steep boundary faults enclose this central, sunken volcanic depression zone. Hydrothermal vent fields cluster along these deep, fractured caldera walls. Axial seamount is one of the most active submarine volcanoes. Significant eruptions occurred in 1998 and 2015. Scientists monitor this location with an extensive, permanent cabled observatory. The Ocean Observatory's initiative provides continuous real-time sensor data. Bottom pressure recorders detect subtle, slow inflation of the seafloor. As magma fills the chamber, the entire volcano slowly swells. Geologist William Chadwick accurately predicted the 2015 volcanic eruption. He observed the precise deformation limits of the volcanic crust. When the crust ruptured, millions of cubic meters erupted outward. Seismometers recorded thousands of tiny, deep earthquakes during the event. The research vessel Thomas Thompson frequently visits these remote waters. Scientists map the newly formed lava flows using multibeam sonar. High-resolution bathymetry reveals the changing, dynamic morphology of ridges. The remotely operated vehicle Jason descends to the dark seafloor. Jason uses robotic arms to collect precise, pristine basalt samples. Geologists analyze these fresh rocks in advanced surface ship laboratories. Electron microprobes determine the exact chemical composition of the glass. These analyses reveal the crystallization history of the deep magma. The submarine Alvin has completed hundreds of scientific dives here. Researchers peering through Alvin viewports observe the fresh lava formations. Paleomagnetism provides another tool for understanding this active spreading center. As basalt cools below the Curie temperature, it records magnetism. Iron minerals align with the prevailing magnetic pole orientation perfectly. The spreading ridge creates symmetrical stripes of magnetic crustal anomalies. These stripes prove the continuous generation of new oceanic crust. The ocean drilling program has extensively bored into this region. Massive drill ships extract long cylindrical cores of solid rock. These layered cores reveal the vertical stratigraphy of the ocean. Layers of soft sediment cover the older basalts on flanks. The sediment thickness increases steadily with distance from the axis. Hydrothermal alteration permanently changes the original, pristine basaltic ocean crust. Olivine minerals slowly transform into soft, green serpentine rock formations. This chemical hydration process releases additional heat into the crust. Chlorite and epidote replace the original igneous mineral crystal structures. These metamorphic changes weaken the solid rock over geological time. Tectonic forces continually fracture this chemically altered, brittle oceanic crust. Earthquakes frequently shake the deep, dark valleys of the center. Extensional faults create a stepped, uneven terrain along the flanks. Abyssal hills run perfectly parallel to the main volcanic axis. These hills represent blocks of crust tilted by tectonic stretching. ROV Jason carries specialized temperature probes to the active vents. Geologist Robert Embley studied these precise thermal measurements for years. The titanium probes penetrate deep into the active chimney walls. They record steep temperature gradients across mere centimeters of rock. The inner wall touches hydrothermal fluid at 300 degrees. The outer wall touches deep seawater at 2 degrees Celsius. This extreme thermal shock drives the rapid mineral precipitation process. Jason also deploys autonomous hydrophones across the rugged, rocky seafloor. These listening devices capture the low, distant rumbles of magma. Acoustic waves travel efficiently through the dense, cold ocean water. Some mineral deposits form massive mounds of solid sulfide rock. The actively venting chimneys grow upward from these basal mounds. When a tall chimney becomes structurally unstable, it eventually collapses. The fallen mineral debris adds to the growing mound volume. Over centuries, these sulfide structures can reach truly enormous proportions. The Endeavour segment of the ridge hosts particularly massive chimneys. Some of these mineral towers rise 50 meters above ground. They look like dark, Gothic cathedrals hidden in the abyss. The heavy metals trapped here represent vast, untapped geological wealth. However, they remain completely undisturbed in their deep, silent environment. As the new crust ages, it undergoes slow chemical weathering. Cold seawater continues to circulate through the upper crustal layers. This low-temperature circulation slowly oxidizes iron within the basalt. The dark gray rocks gradually develop a rusty brown crust. Pelagic sediment begins to accumulate softly on older lava flows. Microscopic shells of dead plankton drift down from the surface. This continuous organic rain mixes with fine airborne dust particles. The sediment blanket thickens at a rate of millimeters slowly. It gradually smooths the rough, jagged contours of volcanic terrain. Eventually, the ancient ridge topography becomes completely buried under mud. The Juan de Fuca plate faces ultimate geological destruction ahead. It slowly moves eastward toward the deep Cascadia subduction zone. Eventually, this dense crust will plunge beneath the American continent. The rocks formed today will eventually melt back into mantle. This grand tectonic cycle takes millions of years to complete. The ridge constantly regenerates what the distant subduction zone consumes. It operates as a perpetual engine of planetary renewal perfectly. The immense heat from the deep earth drives endless motion. Every volcanic eruption adds a new page to geological history. The seafloor slowly spreads, inch by inch, century by century. The deep submergence vehicle Alvin descends into the dark abyss. We reach a depth of 2,200 meters. Outside the viewport, the Juan de Fuca Ridge appears. Floodlights pierce the eternal darkness of the deep ocean. A vast hydrothermal field emerges from the murky shadows. Towering mineral structures rise from the basaltic ocean crust. Oceanographers identify this specific area as the Endeavour segment. It lies roughly 300 miles off the coast. Tectonic plates pull apart here in slow geological motion. Seawater seeps deep into the fractured oceanic crust below. Magma chambers heat this trapped ocean water intensely. The superheated fluid becomes highly buoyant and rises upward. It dissolves precious minerals from the surrounding volcanic rocks. This chemical soup erupts back into the freezing ocean. Upon meeting cold water, the dissolved minerals instantly precipitate. Tiny metallic particles fall out of the fluid suspension. They slowly build the foundations of massive hydrothermal chimneys. Some structures grow remarkably fast in this extreme environment. A chimney might grow 30 centimeters in one single day. Over time, these formations reach staggering vertical heights. We observe the iconic black smoke vents closely now. Dark billowing clouds pour from their jagged mineral summits. This dark smoke is actually a dense particle plume. It contains extremely high concentrations of iron and sulfur. Copper and zinc also mix within this turbulent flow. The fluid exits the vent orifice at extreme velocities. Temperatures inside the black smokers reach 400 degrees. Sometimes the internal heat measures 350 degrees. The water remains liquid only due to crushing hydrostatic pressure. 200 atmospheres of pressure prevent any localized boiling. A sharp temperature gradient exists at the chimney wall. Inside the mineral tube, water sits at 400 degrees. Outside, the ambient seawater remains near 2 degrees Celsius. This massive thermal shift occurs across a few centimeters. The chimney walls provide a thin insulating mineral layer. Scientists map these structures using advanced sonar technology. The remotely operated vehicle Jason glides through the water. Its cameras capture the intricate details of the vents. We can see the highly porous nature of the walls. Hot fluid constantly leaks through these tiny microscopic pores. This creates a shimmering effect in the surrounding water. Researchers from the University of Washington study this site. Dr. John Delaney led many expeditions to these specific coordinates. Dr. Veronique Robigoux painstakingly mapped the massive towering structures. They discovered a famous chimney known as the Godzilla vent. Godzilla stood 40 meters above the ocean floor. It represented the tallest known hydrothermal structure at the time. This height equals a 15-story building under the sea. In 1996, the massive Godzilla structure partially collapsed. Such collapses happen frequently due to structural mineral instability. The base simply cannot support the massive accumulated weight. Following the collapse, Godzilla immediately began to rebuild itself. Within a few years, it grew another 8 meters. This rapid growth highlights the active nature of the ridge. Not all structures emit the characteristic dark metallic smoke. We find intricate formations known as white smokers. White smokers operate at slightly lower temperature ranges. Their fluids usually measure between 200 and 300 degrees. The chemical composition differs greatly from the black smokers. White smoker fluid lacks the heavy iron sulfide concentrations. Instead, it contains abundant barium, calcium, and dissolved silicon. These elements precipitate to form pale and light-colored chimneys. Barium sulfate creates a brilliant white scaffolding underwater. Silica hardens into a glass-like structure over long periods. The resulting chimneys appear almost ghostly in the searchlights. They form on the periphery of the main vent field. Sometimes, white and black smokers exist on the same mound. This indicates complex fluid pathways beneath the ocean floor. The internal anatomy of a chimney reveals distinct mineral zones. The innermost conduit must withstand the highest fluid temperatures. A copper-iron sulfide called chalcopyrite lines this inner channel. Chalcopyrite forms a highly smooth and golden metallic pipe. This pipe channels the superheated water upward without leaking. Outside the chalcopyrite, a layer of zinc sulfide develops. This mineral is known to geologists as sphalerite. The outermost layer consists primarily of calcium sulfate. Scientists refer to this white outer mineral as anhydrite. Anhydrite only remains solid in extremely hot water conditions. If the vent stops flowing, the cold ocean dissolves it. The chimney slowly degrades and crumbles back into sand. The Canadian remotely operated vehicle ROPOS frequently visits here. It collects physical samples using robotic manipulator arms. Titanium syringes draw the pristine hydrothermal fluids for analysis. These fluids contain high levels of dissolved hydrogen sulfide. Methane and helium-3 also bubble up from the mantle. The helium isotope proves the fluid originates deep underground. Heavy metals like manganese enrich the surrounding water column. The rising hot plume eventually reaches neutral buoyancy. It stops rising about 200 meters above the seafloor. Ocean currents then carry this chemical cloud laterally. This creates a massive chemical footprint in the Pacific Ocean. Sensors can detect this plume many kilometers away. The Mothra hydrothermal field lies south of the Endeavour segment. Scientists discovered this unique area in 1996. Mothra contains 5 distinct clusters of active vent chimneys. The structures here exhibit very unusual physical shapes. Many chimneys look like inverted cones or massive mushrooms. They feature large overhanging ledges called hydrothermal flanges. Flanges grow horizontally outward from the main chimney trunk. Hot fluid gets trapped underneath these horizontal rock ledges. This creates inverted pools of shimmering superheated water. The boundary between hot and cold water reflects light perfectly. It looks exactly like a pool of liquid mercury. ROV cameras capture this mesmerizing reflective surface in detail. Fluid slowly percolates upward through the porous flange rock. Minerals precipitate on top, making the ledge thicker over time. Eventually, the trapped water spills over the outer edge. It flows upward like an inverted glowing waterfall. The physical diversity of the Juan de Fuca vents amazes researchers. Some chimneys are slender and delicate like fragile glass. Others form massive, bulky mounds of solid sulfide rock. The Saracen's Head vent features a massive bulbous top. It looks like a giant dome resting on a pillar. The high-rise field contains dozens of closely spaced chimneys. Navigating an ROV through this dense mineral forest requires skill. The pilot must avoid tangling the vital tether cable. One wrong move could easily topple a fragile chimney. Thermocouple probes measure the exact temperatures of the vents. Scientists insert a titanium one directly into the vent orifice. The digital readout immediately jumps to 380 degrees. This confirms the vent remains highly active and powerful. The heat energy released by these fields is truly staggering. A single vent field produces hundreds of megawatts of heat. This equals the output of a small nuclear power plant. The Juan de Fuca Ridge constantly releases the internal heat of Earth. It serves as a crucial cooling mechanism for the planet. We continue our visual survey of the active ridge. The camera pans across a massive fallen chimney column. It lies broken on the basaltic seafloor like ancient ruins. New mineral growth already covers the fractured rocky edges. Tiny localized vents sprout from the surface of the debris. The geological cycle of destruction and rebirth continues endlessly. The hydrothermal system constantly reinvents its physical architecture. No two visits to the ridge ever look exactly identical. The landscape transforms through continuous mineral deposition and collapse. The flow rate of the black smokers varies significantly. Some vents roar like underwater jet engines in the dark. They blast dark fluid upward with incredible physical force. Others merely seep fluid slowly through narrow mineral cracks. The pressure driving this fluid originates deep within the crust. The Juan de Fuca tectonic plate steadily moves eastward. It slowly subducts beneath the massive North American plate. This movement creates continuous fracturing along the spreading center. Earthquakes frequently shake the seabed along the ridge line. These seismic events can instantly alter the hydrothermal plumbing. An earthquake might completely shut off a thriving vent. Alternatively, it could open new fissures in the basalt rock. New black smokers can appear almost overnight after a tremor. Let us observe the delicate exterior of a white smoker. The pale surface looks almost like melting candle wax. Barium sulfate forms smooth, rounded lobes on the chimney exterior. The fluid here flows gently, lacking the violence of black smokers. The lower temperature of 300 degrees changes the chemistry. Metals like copper and iron stay trapped deep underground. Only the lighter elements make it to the ocean floor. This chemical sorting creates the distinct colors of the chimneys. Researchers carefully collect pieces of the white smoker structure. They study the silica layers under powerful electron microscopes. The microscopic structure resembles a complex sponge-like labyrinth. This porosity allows seawater to mix with the vent fluid. The mixing creates unique chemical microenvironments within the walls. The sheer scale of the Endeavour segment is breathtaking. It stretches for many kilometers along the dark ocean floor. Hundreds of individual chimneys populate this massive underwater valley. The acoustic mapping reveals a highly rugged volcanic terrain. Deep fissures slice through the ancient hardened lava flows. The vents align perfectly with these underlying geological faults. They follow the path of least resistance through the rock. The water surrounding the vents appears incredibly cloudy. Suspended mineral particles scatter the bright lights of the ROV. This creates a glowing halo effect around the vehicle. The particulate matter eventually settles like a fine dark snow. It coats the surrounding basalt in a thick metallic blanket. Core samples reveal thousands of years of this steady accumulation. Massive sulfide deposits form deep beneath the vent fields. These deposits contain millions of tons of valuable heavy metals. They represent concentrated versions of the deep mantle of the Earth. The axial seamount provides another fascinating area of study. It represents an active underwater volcano on the ridge. A massive caldera sits at the summit of this seamount. Hydrothermal vents ring the interior walls of this sunken caldera. The structures here differ slightly from the Endeavour segment. They tend to be shorter and much more fragile. Fresh lava flows frequently pave over the axial seamount vents. The volcanic activity constantly resets the hydrothermal geological clock. Scientists deployed continuous monitoring instruments at this specific site. Cabled observatories stream live data back to the mainland. Sensors record fluid temperatures every single second of the day. They monitor the subtle changes in the chimney pressure. This allows oceanographers to predict upcoming volcanic eruptions accurately. The physical environment of Juan de Fuca remains deeply alien. The crushing pressure and extreme heat defy human comprehension. Yet, a strange mathematical order governs the chimney growth. Fluid dynamics dictate the precise shape of the mineral flanges. Thermodynamics control the exact precipitation of the metal sulfides. The chimneys stand as monuments to these fundamental physical laws. They represent a perfect balance between fire and freezing water. The bright lights of the submersible finally begin to dim. Battery power runs low after hours of careful scientific observation. The vehicle slowly rises away from the dark Endeavour segment. These hidden monuments of extreme heat will grow in darkness. The dark ocean below hides a very complex chemical reality. Invisible dissolved elements shape this very quiet deep underwater world. The Juan de Fuca Ridge possesses a unique fluid chemistry. These deep-sea hydrothermal vents act as massive chemical reactors. Superheated liquid water strips minerals from the dense basaltic crust. This heavily altered fluid eventually escapes back into cold seawater. Scientists use titanium syringes to capture these pristine vent fluids. The submersible Alvin collected pure vent water many decades ago. Researchers found an extremely harsh chemical environment hidden down here. The measured pH levels of these deep fluids remain low. Pure vent fluid often registers a highly acidic pH value. This intense acidity rivals that of common household cooking vinegar. Surrounding ocean seawater usually maintains a stable alkaline pH level. The stark contrast creates a very sharp chemical boundary layer. Heavy metals dissolve quite easily in this highly acidic fluid. Iron and dissolved zinc remain suspended in the hot solution. At 2,000 meters deep, extreme pressure alters chemical rules. Salinity within the vent fluids varies quite dramatically down here. Normal seawater contains roughly 35 parts per thousand salt. Juan de Fuca vent fluids sometimes show twice this salinity. Extreme subterranean heat causes seawater to undergo rapid phase separation. This physical process resembles a deep ocean thermal distillation system. Boiling water deep in the oceanic crust separates into fractions. A dense salty brine sinks much lower into the rocks. A lighter vapor phase rises quickly toward the dark seafloor. Vent chimneys emit either the heavy salty brine or vapor. The main Endeavour field releases mostly lighter vapor phase fluids. These vapor fluids possess significantly lower background oceanic salt concentrations. Salinity down here can drop to half of normal seawater. The chemical signature changes with every minor deep tectonic earthquake. Hydrogen sulfide represents the most crucial dissolved vent gas present. This toxic compound provides vital energy for the entire ecosystem. Concentrations reach up to 6 millimoles per kilogram down here. Surface ocean waters contain almost zero dissolved hydrogen sulfide gas. The high gas concentration creates a distinct rotten egg smell. Scientists smell this volatile gas when bringing samples aboard ships. The research vessel Atlantis processes these volatile water samples immediately. Chemical reactions happen quickly once deep ocean crushing pressure releases. Methane gas also bubbles from these deeply cracked volcanic rocks. Juan de Fuca hydrothermal vents release substantial amounts of methane. Methane concentrations hover around 2 millimoles per kilogram deep underwater. This specific methane forms through purely abiotic subterranean geological processes. Seawater reacts directly with green olivine minerals in the crust. This specific chemical reaction is widely known as deep serpentinization. Iron oxidation during this geological process releases free hydrogen gas. Carbon dioxide then combines with this newly freed hydrogen gas. This combination produces methane without any biological cellular assistance whatsoever. Geochemist John Delaney studied these specific gas concentrations quite extensively. His research team deployed mass spectrometers directly on the seafloor. In situ measurements prevent trapped gases from escaping during transport. The underwater sensors record subtle chemical fluid changes every second. Comparing vent fields reveals fascinating global deep-sea chemical differences. The East Pacific Rise vents exhibit entirely different chemical signatures. Those southern vents produce much higher dissolved iron fluid concentrations. Juan de Fuca vent fluids contain significantly more dissolved silica. Silica precipitates out to form beautiful glassy underwater mineral deposits. The distant mid-Atlantic ridge sits on much older rock. Fluids there interact with deeper mantle rock formations instead today. This deeper rock interaction creates a completely different mineral output. The Lost City hydrothermal field provides another sharp chemical contrast. Lost City vents produce highly alkaline warm water fluids instead. Their measured pH levels reach an incredibly basic 11 value. Juan de Fuca remains strictly an acidic hot vent system. The extreme temperature profile also dictates the local fluid chemistry. Water emerges at nearly 350 degrees Celsius. At this extreme temperature, magnesium completely drops out of seawater. The descending seawater loses all its original dissolved magnesium content. Zero dissolved magnesium is a hallmark of pure hydrothermal fluid. Researchers use magnesium levels to calculate vent fluid purity accurately. Any detectable magnesium indicates mixing with cold background ocean seawater. The ROV Jason routinely performs these crucial underwater magnesium checks. Remote manipulators hold temperature probes inside the dark vent orifices. Accurate temperature readings ensure correct chemical equilibrium calculations happen later. Helium isotopes provide another vital clue for studying deep geochemists. Mantle rocks contain rare helium-3 stable isotope gas signatures. The Juan de Fuca vents release this trapped helium-3. This primordial gas has been trapped since early Earth formed. Measuring helium helps track the deep ocean global circulation patterns. The chemical plume drifts horizontally for hundreds of dark kilometers. Oceanographers track this invisible chemical cloud through the vast Pacific. Dissolved iron from the deep vents fertilizes distant ocean regions. This iron supports microscopic plankton growth near the ocean surface. The deep sea chemistry directly impacts the upper ocean ecosystem. Carbon dioxide levels in the pure vent fluid are massive. Concentration exceeds surface water levels by 50 times down here. This dissolved carbon feeds the local microbial vent biological populations. Chemosynthetic bacteria consume the carbon dioxide and toxic hydrogen sulfide. They convert these harsh chemicals into usable organic biological matter. The entire deep ocean food web relies on chemical synthesis. Heavy metals present a toxic challenge to most marine life. Copper and lead flow freely from the towering black smokers. Cadmium concentrations reach dangerous levels near the hot vent openings. Yet the local deep fauna has adapted to this toxicity. Specialized animal proteins bind the heavy toxic metals safely away. The chemical environment changes rapidly as the hot fluid cools. Rapid cooling forces dissolved minerals to precipitate almost instantly underwater. This constant precipitation builds the towering sulfide mineral chimneys eventually. A single mineral chimney can grow several centimeters each day. The exact mineral composition determines the visual color of smoke. Black smokers contain very high levels of dark iron sulfides. White smokers emit lighter-colored barium and calcium mineral deposits. The Juan de Fuca Ridge features mostly dark black smokers. The axial seamount segment displays unique chemical fluid properties today. Recent volcanic eruptions there altered the fluid chemistry completely overnight. An underwater eruption in 2015 reset everything chemically. Post-eruption fluids showed massive new spikes in carbon dioxide. Hydrogen sulfide levels also tripled immediately following the volcanic eruption. These chemical pulses trigger massive bacterial blooms deep underwater quickly. White bacterial mats cover the fresh black underwater lava flows. The water chemistry gradually stabilizes over the following few years. Long-term observatories monitor this slow chemical deep relaxation process. Cable sensors send chemical data to shore via fiber optics. Scientists watch the fluid chemistry evolve in perfect real time. The cleft segment offers a different chemical environment entirely today. Fluids here are cooler and heavily diluted by cold seawater. The fluid temperature rarely exceeds 200 degrees Celsius there. Lower temperatures prevent certain heavy metals from dissolving completely underwater. Copper remains safely trapped deep within the solid crustal rocks. Zinc becomes the dominant dissolved heavy metal at this location. The resulting mineral chimneys display a lighter gray visual coloration. Geologist Deborah Kelly has extensively mapped these deep chemical zones. Her detailed work reveals a highly structured complex chemical architecture. Fluid chemistry dictates exactly where specific vent animals can live. Tube worms prefer areas with high hydrogen sulfide toxic fluid flow. Snails gather where the toxic fluid is sufficiently diluted naturally. The steep chemical gradient creates distinct biological animal zoning patterns. Dissolved oxygen is completely absent from the pure vent fluid. Oxygen only appears when cold background ocean seawater mixes in. This turbulent mixing zone creates a delicate chemical biological balance. Animals must position themselves exactly within this narrow mixing gradient. Vent fluid excess causes lethal thermal and sudden chemical shock. Too much seawater deprives them of essential chemical food energy. The chemical boundary layer fluctuates with the deep ocean tides. Lunar cycles subtly influence the upward flow of these chemicals. Pressure changes from ocean tides squeeze the porous crustal rocks. This gentle squeezing slightly alters the chemical fluid output daily. The total chemical complexity of Juan de Fuca truly astounds. Every vent structure possesses a completely unique chemical fluid fingerprint. The Mothra hydrothermal field vents highly concentrated saline water fluids. These dense salty fluids pool in depressions on the seafloor. Small inverted lakes of salty heavy brine form in darkness. The dense brine reflects the lights of the visiting submersibles. Ammonia is another chemical compound found in these heated waters. It forms when ancient organic matter is deeply thermally degraded. Buried marine sediments cook in the extreme deep geothermal heat. The resulting ammonia provides essential nitrogen for local vent bacteria. Without this dissolved nitrogen, biological cellular growth would simply stop. Phosphorus also emerges from the dissolving deep ocean basaltic rocks. This essential nutrient supports the complex biological synthesis of DNA. The hydrothermal vents provide a complete chemical cocktail for life. Trace elements like heavy cobalt and nickel are also present. These rare metals act as vital catalysts for bacterial enzymes. The concentration of dissolved manganese is particularly high down here. Manganese chemical plumes can be tracked for incredible oceanic distances. Scientists use manganese traces to locate undiscovered deep vent fields. The chemical sensors act like mechanical bloodhounds deep underwater today. They sniff out the faintest chemical traces of dissolved metals. The Juan de Fuca system continuously alters global ocean chemistry. Over millions of years, vents chemically cycle the entire ocean. All seawater eventually passes through a hot hydrothermal vent system. This massive filtration process removes dissolved magnesium and adds iron. The chemical balance of the global ocean depends heavily here. Without these deep vents, the sea would become chemically toxic. The ocean crust absorbs excess sodium during the heating process. Chemical buffering keeps the marine environment completely stable almost forever. The Endeavour segment alone hosts hundreds of active mineral chimneys. Each chimney contributes to this massive global ocean chemical exchange. The fluid velocity affects the local chemical spatial distribution patterns. Fast-flowing black smokers shoot chemicals high into the water. The chemical plume rises until it achieves neutral density buoyancy. Slower diffuse flows gently seep through the cracked oceanic basalt. Diffuse fluids are much cooler and chemically quite distinct today. They have already mixed with cold seawater beneath the crust. This subsurface mixing creates a hidden underground biosphere of microbes. Microbes alter the fluid chemistry before it even emerges upward. They consume some hydrogen gas and produce extra methane gas. The fluid arriving at the seafloor is heavily biologically altered. Disentangling biological and geological chemistry remains a very difficult task. Researchers utilize stable isotope analysis to solve this chemical puzzle. Carbon-13 atom ratios reveal the true origin of methane. In 1998, a massive underwater volcanic eruption occurred here. Fresh lava paved over a previously well-studied biological vent community. Scientists returned to the exact geographical coordinates shortly after eruption. The specific location was 45 degrees and 55 minutes north. They fully expected to find a completely lifeless volcanic wasteland. Instead, they witnessed the incredibly rapid biological colonization of lava. Within mere months, new white bacterial mats coated cooling rocks. Shortly after that, tiny tube worm larvae began settling in droves. This remarkable event proved the incredible resilience of deep life. Oceanographer Robert Embley documented this rapid biological succession with care. His scientific team photographed the changing volcanic landscape over years. They watched a barren black rock transform into a city. The internal chemistry of the giant tube worm is highly complex. Their red blood contains special hemoglobin molecules for gas transport. This unique hemoglobin binds simultaneously to oxygen and hydrogen sulfide. Normally, dissolved hydrogen sulfide is instantly deadly to animal life. It binds directly to respiratory enzymes and halts cellular respiration. But the tube worm hemoglobin prevents this toxic chemical reaction completely. It safely escorts the dangerous sulfide directly to internal bacteria. The bacteria then perform the truly magical act of chemosynthesis. The Juan de Fuca Ridge harbors a completely alien biological community. This ecosystem thrives in total darkness at immense ocean depths. Sunlight never reaches these volcanic valleys 2,000 meters down. Photosynthesis cannot exist within this cold and pressurized abyssal environment. Instead, life relies entirely on a process known as chemosynthesis. Chemical energy replaces solar energy as the foundation of life. Superheated fluids emerge from the seafloor at extreme high temperatures. These hydrothermal fluids carry dissolved minerals and toxic hydrogen sulfide. Most terrestrial organisms would perish instantly in this chemical soup. Yet, specialized microbes consume these toxic compounds to generate energy. This microscopic metabolic process supports a vast and complex food web. Biologists consider this location the most extensively studied hydrothermal system. Decades of research reveal a highly structured and unique biosphere. Microbiologist Holger Janusz first theorized this deep ocean microbial metabolism. He studied water samples recovered by the submersible vehicle Alvin. These samples contained high concentrations of unique sulfur-oxidizing bacteria. The bacteria extract electrons from hydrogen sulfide to fix carbon. This chemical reaction creates organic molecules necessary for cellular growth. Free-living bacterial mats blanket the basalt rocks near active vents. These thick white mats resemble fresh snow on the dark seafloor. Grazing organisms feed directly on these dense microbial carpets. However, the most successful animals employ a different survival strategy. They house the bacteria directly inside their own living tissues. This internal farming creates a highly efficient symbiotic energy exchange. The dominant species here is the tubeworm Ridgeopisces. These pale worms grow in dense thickets around hydrothermal chimneys. A single cluster can contain thousands of individual living tubes. Scientist Colleen Cavanaugh unlocked the secret of their biological success. She discovered that these worms completely lack a digestive system. They possess no mouth, no stomach, and no intestinal tract. Instead, their bodies contain a specialized organ called a trophisome. Billions of symbiotic bacteria live packed tightly inside this organ. The worm absorbs raw chemicals from the surrounding vent fluid. It delivers these chemicals directly to the internal bacterial colony. In return, the bacteria produce pure carbon nutrients for the worm. Transporting these chemicals requires a highly specialized circulatory system. Ridgeopisces possesses bright red plumes extending from its tube. These delicate gills act as the primary chemical exchange surface. The worm's blood contains a unique and complex hemoglobin molecule. This hemoglobin binds simultaneously to both oxygen and hydrogen sulfide. Normally, sulfide compounds instantly destroy traditional oxygen-carrying blood cells. The tubeworm hemoglobin protects the animal from this chemical toxicity. It safely transports the volatile mixture deep into the trophisome. This elegant evolutionary adaptation allows massive biological growth rates. Some tubeworms extend their protective casings by several feet annually. They form the structural foundation of the entire ridge ecosystem. These dense tubeworm bushes create vital habitats for other creatures. Tiny palmworms navigate the narrow spaces between the tubes. Depressurized limpets cling tightly to the smooth biological surfaces. These small mollusks graze continuously on the exterior bacterial films. Scale worms patrol the thickets in search of organic debris. They represent the primary consumer level of this deep web. Energy moves efficiently from the microbes to these small invertebrates. The sheer density of life here rivals tropical coral reefs. Biomass concentrations reach tens of kilograms per square meter. This abundance sharply contrasts with the barren surrounding abyssal plain. Just meters away, the seafloor resembles an empty desert landscape. Secondary consumers actively hunt within this concentrated biological oasis. White vent crabs scuttle across the jagged volcanic basalt rocks. These scavengers consume dying tube worms and fallen organic material. Spider crabs use long delicate legs to traverse the chimneys. They carefully extract soft invertebrates from protective rocky crevices. Pink eelpout fish swim lazily through the shimmering warm water. These zooarcid fish prey on small crustaceans and floating amphipods. They tolerate water temperatures that would quickly boil surface fish. Their slow movements conserve energy in this high-pressure environment. Every calorie matters in the cold depths of the ocean. The food web remains tightly bound to the vent fluid. Apex predators occasionally visit these isolated deep ocean communities. Pale octopuses glide silently above the active hydrothermal chimney fields. They search for careless crabs wandering too far from cover. Deep sea skates circle the perimeter of the warm water plumes. These large cartilaginous fish hunt along the dark ecosystem margins. However, they cannot remain in the toxic vent water permanently. They merely harvest energy from the edges of the colony. The core of the ecosystem belongs entirely to endemic species. Endemic creatures exist exclusively at these specific hydrothermal vent sites. They have evolved in complete genetic isolation for millions of years. The Juan de Fuca Ridge serves as their only universe. Scientists constantly measure the energy transfer within this closed system. Researchers deploy the remotely operated vehicle Jason for this task. Jason carries precise instruments to sample the biological chemistry. They analyze the carbon isotopes present in animal tissue samples. These chemical signatures prove the pure chemosynthetic origin of life. No carbon from surface photosynthesis reaches these deep vent animals. The surface marine snow provides zero nutritional value here. The entire food web sustains itself independently from the sun. This absolute isolation fascinates evolutionary biologists and marine ecologists alike. It proves that life can flourish using only planetary heat. Earth's internal geological engines drive this remarkable biological productivity. Different vent sites on the ridge host distinct biological variations. The axial seamount sits at 45 degrees north latitude. This massive underwater volcano supports incredibly diverse microbial populations. Here, iron oxidizing bacteria thrive alongside the standard sulfur-consuming microbes. They extract energy from dissolved iron emerging from the crust. These bacteria form thick orange crusts on the cooling lava. The orange mats create a secondary parallel food chain structure. Specialized nematodes feed exclusively on these iron-rich bacterial deposits. This expands the overall ecosystem complexity at the axial site. Energy flows through multiple parallel chemical pathways simultaneously. The biological diversity directly mirrors the underlying geological chemistry. Further north lies the famous Endeavour segment of the ridge. This area features massive sulfide chimneys towering above the seafloor. Some structures reach heights of 40 meters into the dark. The water depth here plunges past 2,200 meters. Extreme pressure keeps the superheated vent fluids from immediately boiling. Temperatures inside the chimney walls exceed 350 degrees Celsius. Yet, life pushes incredibly close to this lethal thermal boundary. Thermophilic archaea colonize the porous interior rocks of the chimneys. These ancient organisms survive at temperatures exceeding 100 degrees. They form the absolute base of the high-temperature food web. Their heat-resistant enzymes hold massive potential for modern biotechnology. Oceanographer John Delaney spent decades mapping these endeavor segment communities. He documented how the ecosystem changes over long temporal scales. Hydrothermal vents are not permanent geological features on the seafloor. Earthquakes frequently alter the subterranean plumbing of the ocean crust. Fluid flow can suddenly stop, instantly killing the dependent community. Without hydrogen sulfide, the symbiotic bacteria quickly starve and die. The magnificent tubeworm forests wither away into empty white shells. Scavengers quickly consume the remaining decaying organic matter. Soon, the once thriving vent becomes a silent graveyard of calcium. This cycle of death demonstrates the fragility of chemosynthetic life. The ecosystem relies completely on continuous geological fluid delivery. Conversely, volcanic eruptions can create entirely new hydrothermal vent fields. Fresh lava flows sterilize the immediate surrounding ocean floor area. However, biological recolonization begins almost immediately after the rocks cool. A hidden subsea-floor biosphere plays a crucial role in recovery. Vast networks of microbes live deep within the porous basalt. Warm fluids flush these subterranean bacteria out into the ocean. They quickly settle on the fresh lava to form new mats. These pioneer microbes prepare the toxic environment for larger animals. Microbial films detoxify the immediate water chemistry near the rocks. This invisible process allows the first invertebrate larvae to settle. Life aggressively reclaims the newly forged volcanic real estate. The first macroscopic animals to arrive are usually mobile scavengers. Amphipods swarm the new bacterial blooms in massive dense clouds. Shortly after, juvenile tubeworms attach themselves to the fresh basalt. These larvae drift in the deep ocean currents for weeks. They sense the specific chemical signatures of active hydrothermal venting. Once settled, they immediately begin farming their internal bacterial symbionts. The ecosystem succession proceeds with remarkable speed and predictable order. Within 3 years, a mature tubeworm forest dominates the landscape. The complex food web fully re-establishes itself in total darkness. This rapid biological resilience astounds marine biologists monitoring the ridge. It highlights the aggressive adaptability of deep ocean vent organisms. Comparing this ridge to other global vent systems reveals stark differences. The Mid-Atlantic ridge hosts ecosystems dominated by blind swarming shrimp. Those Atlantic vents completely lack the massive tubeworm forest seen here. The Juan de Fuca Ridge remains the undisputed kingdom of worms. Geographic isolation prevents the mixing of these distinct ocean populations. Deep ocean currents act as invisible barriers between the ridges. Consequently, unique evolutionary pathways unfold in each dark abyssal basin. The Pacific vent communities developed their own highly specialized hierarchy. Every organism here fills a precise and necessary ecological niche. Nothing goes to waste in this nutrient-poor deep ocean desert. Biological recycling operates at maximum efficiency near the vent chimneys. Even the chemical waste products of one species sustain another. Methane gas bubbles up from the deeper sediment layers constantly. Methanotrophic bacteria consume this gas to produce heavy organic carbon. Deep-sea clams filter these specific bacteria directly from the water. These large bivalves embed themselves in the warm sediment cracks. Their thick white shells protect them from predatory crab claws. They represent another crucial node in the localized food web. The clams grow extremely slowly compared to the rapid tube worms. Some individual specimens live for more than 100 years. They silently record the chemical history of the vent fluid. Their shell growth rings act like submerged geological time capsules. The entire Juan de Fuca ecosystem operates in delicate equilibrium. Geothermal energy continuously pushes upward from the Earth's molten mantle. This heat initiates the chemical reactions necessary for biological survival. Microbes capture the chemical potential before it dissipates into seawater. Invertebrates harvest the microbes to build complex physical tissue structures. Predators consume the invertebrates to maintain population balances over time. When the geological heat finally fades, the biological community vanishes. The surviving larvae simply drift away into the freezing darkness. They float silently until they find another active hydrothermal chimney. This nomadic existence defines the ultimate reality of vent life. It is a beautiful, fragile dance of geology and biology. The Juan de Fuca Ridge perfectly illustrates this profound connection. It remains our greatest window into a truly alien biosphere. Scientific exploration here continues to rewrite our understanding of life. The deep ocean still holds countless undiscovered biological secrets tonight. New sensing technologies constantly monitor these remote biological communities now. Underwater cabled observatories transmit live ecological data back to surface laboratories. High-definition cameras carefully capture the slow movements of the deep web. Sensitive acoustic sensors record the subtle sounds of shifting volcanic crust. Advanced chemical probes track the fluctuating concentrations of dissolved ocean minerals. This continuous observation provides unprecedented insight into deep marine biology. We no longer rely solely on brief and isolated submarine dives. The dark ridge ecosystem is finally revealing its long-hidden temporal rhythms. Every single new data point deepens our appreciation for this world. The scientific history of the Juan de Fuca Ridge is vast. Decades of rigorous exploration have transformed this dark abyss. It now stands as the most monitored submarine volcano on Earth. Early mapping efforts began in the late 1970s. Oceanographers utilized primitive sonar to trace the tectonic boundary. They discovered a jagged mountain range hidden deep underwater. The first major breakthrough occurred in 1981. Researchers aboard the vessel Melville detected strange temperature anomalies. The water column showed unusual spikes in dissolved manganese. This chemical signature strongly indicated active hydrothermal venting below. By 1983, targeted visual confirmation was finally required. Scientists deployed the Deep Submergence Vehicle Alvin for this mission. The titanium sphere carried 3 occupants safely to the seafloor. They descended to a depth of 2,200 meters. The ambient water temperature outside dropped to 2 degrees Celsius. Alvin switched on its external halogen lights near the bottom. The crew observed towering sulfide structures venting thick black smoke. Geologist Alexander Malahov documented these massive mineral deposits very carefully. The chimneys measured over 15 meters in total vertical height. Fluid temperatures exiting the vents exceeded 300 degrees Celsius. In subsequent years, the Endeavour segment became a primary focus. Oceanographer John Delaney championed extensive research at this specific location. His vision involved turning the ridge into an underwater laboratory. During 1984, Alvin completed several mapping transects here. The submersible navigated through treacherous fields of active hydrothermal chimneys. Pilots had to avoid melting the thick acrylic viewing ports. They maintained a safe distance from the superheated fluid plumes. Researchers collected pristine mineral samples using hydraulic manipulator arms. Geochemist Meg Tivy later analyzed these highly fragile sulfide crusts. Her work revealed complex internal gradients of temperature and chemistry. Human-occupied submersibles offered incredible first-hand observation capabilities. However, their bottom time was strictly limited by battery life. A typical Alvin dive allowed only 4 hours of actual work. Science required longer periods of uninterrupted observation and physical sampling. The introduction of remotely operated vehicles changed deep ocean research. The robotic vehicle Jason became a frequent visitor to the ridge. Operated via a long tether, Jason could work for several days. Its fiber optic cable transmitted high-definition video to the surface. Pilots aboard the research vessel Thomas G. Thompson controlled its movements. They executed precise sampling maneuvers with robotic force feedback arms. Axial seamount soon emerged as a crucial site for marine volcanologists. This prominent underwater volcano sits directly over a deep mantle hotspot. It rises 700 meters above the surrounding rocky ridge axis. Geologist William Chadwick began studying its inflation and deflation cycles. He deployed precise bottom pressure recorders across the flat caldera floor. These instruments measured tiny changes in the depth of the seafloor. As magma filled the chamber below, the caldera floor rose upwards. Chadwick noted an upward movement of 15 centimeters per single year. He successfully predicted the 1998 submarine volcanic eruption. This marked a major milestone in global submarine volcanic forecasting. The 1998 event provided unprecedented and valuable scientific data. The research vessel Atlantis quickly mobilized to the remote eruption site. Scientists lowered a towed camera system to survey the geological damage. They found fresh lava flows covering previously mapped hydrothermal active vents. The new basaltic rock was glassy and completely devoid of sediment. Microbial blooms formed thick white mats over the rapidly cooling lava. Researchers deployed specialized titanium syringes to sample the warm vent fluids. They discovered unique microbial communities thriving in the newly created habitat. This rapid response mission proved the dynamic nature of the ridge. The seafloor was constantly changing shape through violent deep geological processes. Brief expeditionary cruises were no longer sufficient for comprehensive ecosystem understanding. The oceanographic community proposed a radical new technological approach for research. They envisioned a permanent cabled observatory spanning the entire tectonic plate. This ambitious project was formally named the Ocean Observatories Initiative. The cabled array component focused directly on the Juan de Fuca plate. Installation required laying hundreds of kilometers of submarine fiber optic cable. The specialized cable ships worked tirelessly during the summer of 2014. They plowed the heavy lines into the soft sediment of the abyssal plain. This infrastructure connected the deep sea directly to coastal shore stations. It provided unprecedented continuous electrical power and massive digital data bandwidth. Primary nodes were installed at strategic locations along the active ridge. These massive titanium structures serve as deep ocean electrical power substations. They step down the 10,000 volts transmitted from the distant coast. Secondary nodes distribute this power to individual scientific monitoring instruments. The remotely operated vehicle ROPOS was instrumental in connecting these delicate systems. Pilots used precise robotic arms to plug in wet mateable connectors. These specialized cables can be safely joined underwater without electrical shorting. The network provides continuous power to dozens of complex scientific sensors. Researchers no longer rely on limited battery packs for their deep equipment. The ridge is now bathed in a constant stream of reliable electricity. Axial seamount hosts the most dense concentration of these monitoring instruments. A network of broadband seismometers listens to the Earth absolutely continuously. They detect micro-earthquakes deep within the subterranean liquid magma chamber. High-resolution tilt meters measure the microscopic physical breathing of the volcano. These devices can detect a shift of a fraction of a millimeter. Benthic mass spectrometers analyze the chemical composition of hot vent fluids. They measure dissolved gases like hydrogen sulfide and methane completely automatically. Acoustic Doppler current profilers monitor the flow of cold ocean water. They track how hydrothermal plumes disperse into the surrounding water column. All this data flows through the glass fibers at the speed of light. The data arrives at a facility in Seattle within mere milliseconds. Scientists can watch high-definition video of deep-sea vents live. Anyone with an internet connection can view the hydrothermal chimneys remotely. This open data policy has revolutionized modern deep-sea oceanography practices. In April 2015, the system proved its immense scientific value. The seismometers detected a sudden massive swarm of deep crustal earthquakes. Thousands of small tremors shook the caldera over 24 hours. The tilt meters recorded a rapid drop in the overall seafloor elevation. The caldera floor fell by 2.4 meters almost instantly. The instruments captured a submarine volcanic eruption in absolute real time. This real-time observation had never been achieved before anywhere globally. The array survived the violent geological event without any major damage. Subsequent expeditions mapped the newly erupted lava flows with great precision. The autonomous underwater vehicle Sentry was deployed to survey the affected area. Sentry flies 50 meters above the seafloor using multibeam mapping sonar. It created bathymetric maps with a resolution of exactly 1 meter. The data revealed a massive new lava flow on the northern volcanic rift. The flow was over 120 meters thick in certain places. It had buried several older monitoring instruments under fresh molten rock. The scientific community gained invaluable new insights into oceanic crustal formation. Beyond geology, expeditions focus heavily on hydrothermal fluid chemical analysis. Specialized tools are required to sample water at 300 degrees. The isobaric gas-tight sampler is considered a marvel of engineering. It maintains the extreme pressure of the deep ocean during vertical ascent. This prevents dissolved volatile gases from bubbling out of the fluid sample. Geochemists extract the pristine samples inside pressurized shipboard laboratory chambers. They analyze the specific isotopic signatures of dissolved helium and carbon. These isotopes reveal the deep mantle origins of the rising venting fluids. The ratio of helium-3 to helium-4 is particularly scientifically important. It indicates the presence of primordial gases trapped since Earth first formed. Biological expeditions also frequent the Juan de Fuca Ridge very regularly. Researchers study the unique evolutionary adaptations of endemic hydrothermal vent fauna. They use specialized suction samplers to gently collect highly fragile tube worms. Slurp guns pull the organisms into clear acrylic underwater holding chambers. The creatures are brought to the surface in heavily insulated bio-boxes. This maintains the extreme cold temperature required for their biological survival. Microbiologists focus on the invisible life thriving within the hard rock crust. They deploy colonization chambers near the most active hot venting sites. These small titanium mesh boxes contain perfectly sterile natural basalt chips. Microbes from the vent fluid slowly colonize the artificial rocky substrate. The chambers are left on the seafloor for an entire calendar year. The following summer, an ROV retrieves the incubated samples very carefully. Scientists sequence the DNA of the newly established marine microbial communities. They discover novel metabolic pathways used for biological chemosynthesis in the dark. Some expeditions focus on the vast subsea floor biosphere hidden deep below. Researchers drill shallow boreholes directly into the young oceanic basaltic crust. They install specialized cork observatories to completely seal the deep drill holes. These corks allow scientists to draw pristine fluids from deep within the rock. The subsea floor fluids harbor entirely different microbial populations than the surface vents. This hidden ecosystem may represent the largest contiguous microbial habitat on Earth. The Endeavour hydrothermal vents represent a unique and complex management challenge. This segment was designated as a marine protected area by the Canadian government. Scientific research here must be carefully coordinated and strictly legally regulated. Expeditions must avoid damaging the towering, highly fragile sulfide mineral structures. The ROV Doc Ricketts conducted high-resolution visual surveys of this zone. It utilized a downward-facing laser scanner to precisely map the chimneys. The resulting three-dimensional digital models are incredibly detailed and highly accurate. They reveal the complex structural morphology of massive edifices like Godzilla. This mapping provides a critical baseline to monitor future structural chimney collapse. Natural seismic activity frequently topples these massive and unstable mineral towers. The surface fleet supporting these deep operations is highly technologically advanced. The research vessel Atlantis spans 274 feet in length. It features specialized heavy handling systems for launching submersibles very safely. The dynamic positioning system holds the massive ship steady in rough seas. Powerful thrusters counteract the strong surface currents of the northern Pacific Ocean. The vessel remains locked on specific geographic coordinates during deep-sea dives. The research vessel Sikuliak also frequents the Juan de Fuca Ridge region. Its ice-strengthened hull is designed for harsh and unforgiving northern environments. The ship boasts a spacious aft deck for staging heavy scientific equipment. A massive A-frame crane lifts multi-ton sensor packages directly over the stern. Modern expeditions also study the dynamic water column far above the ridge. The hydrothermal plumes rise hundreds of meters before spreading out laterally. Acoustic sonars mounted on the ship hull track these thermal anomalies continuously. The sound waves reflect off the suspended microscopic metallic mineral particles. This creates a visual representation of the otherwise invisible chemical cloud. Scientists deploy rosettes equipped with conductivity, temperature, and depth measuring sensors. These CTD packages are lowered straight through the rising warm hydrothermal plume. Automated bottles snap shut at specific targeted depths to capture water samples. The samples help map the oceanic dispersion of deep geothermal heat and chemicals. This physical process influences the broader oceanographic circulation of the entire Pacific. The Juan de Fuca Ridge offers a unique geological perspective. It differs greatly from other global mid-ocean spreading centers. The East Pacific rise spreads at a very rapid pace. That southern ridge moves up to 15 centimeters annually. In contrast, Juan de Fuca is an intermediate spreading ridge. It separates at roughly 6 centimeters per year. This moderate speed creates distinct hydrothermal vent architectures. Magma chambers beneath Juan de Fuca are relatively stable. They provide a steady heat source for the circulating fluids. Slow-spreading ridges like the Mid-Atlantic Ridge behave differently. They feature deep rift valleys and highly episodic volcanic activity. Juan de Fuca strikes a perfect balance between these extremes. Depth also separates Juan de Fuca from other global sites. The Mid-Atlantic Ridge vents often sit 3,000 meters deep. Juan de Fuca vents rest at about 2,200 meters. This shallower depth slightly reduces the ambient hydrostatic pressure. Fluid chemistry varies significantly across these different ocean basins. Atlantic vents often emit fluids rich in iron and copper. Juan de Fuca fluids contain higher concentrations of dissolved hydrogen. The Pacific vents host giant tube worms called Riftia pachyptela. Atlantic vent ecosystems rely more on swarms of blind shrimp. Indian Ocean vents combine species from both major ocean basins. Juan de Fuca remains the most intensely studied system globally. Decades of continuous observation provide unmatched baseline environmental data. This intense study led to crucial conservation efforts right here. In 2003, Canada established a marine protected area. The Endeavour Hydrothermal Vents Marine Protected Area covers specific coordinates. It sits near 47 degrees north and 129 degrees west. This was the first protected area of its kind globally. The sanctuary encompasses roughly 97 square kilometers of seafloor. It protects a high concentration of active hydrothermal chimneys. Conservationists recognize the extreme fragility of these deep ocean ecosystems. Trawl fishing poses a minimal threat at these great depths. However, scientific research itself required careful regulation and continuous monitoring. Submersibles can easily crush delicate tube worm colonies by mere accident. A larger threat looms over these global hydrothermal vent systems. Deep-sea mining companies seek valuable metals on the seafloor. Polymetallic sulfide deposits accumulate around active and extinct vent chimneys. These deposits contain exceptionally rich veins of copper and zinc. Trace amounts of gold and silver also precipitate right here. Mining operations would deploy massive robotic cutters to the seafloor. These machines would grind the ancient chimneys into fine slurry. Such actions would instantly destroy the localized biological vent communities. The Endeavour protected area prevents any commercial extraction within borders. Other sections of the Juan de Fuca Ridge remain vulnerable. International seabed authorities continue to debate deep ocean mining regulations. These protected vents hold crucial clues to our biological origins. Many scientists believe life began in similar deep hydrothermal environments. The primordial ocean lacked a protective ozone layer above it. Ultraviolet radiation bombarded the surface of the early Earth constantly. The deep ocean offered a safe refuge from this radiation. Hydrothermal vents provided all the necessary ingredients for early life. They supplied continuous heat energy from the deep planetary interior. They offered abundant chemical compounds dissolved in the hot fluids. The mixing of hot vent fluid and cold seawater creates gradients. These chemical gradients act like natural batteries on the seafloor. Scientist Michael Russell proposed the alkaline hydrothermal vent origin hypothesis. He suggested life emerged from tiny pores in vent chimneys. These pores trapped complex organic molecules in highly concentrated spaces. Iron and sulfur compounds lined the walls of these microscopic chambers. The minerals acted as natural catalysts for early chemical reactions. They facilitated the formation of simple amino acids and peptids. The temperature gradient across the chimney walls drove these reactions. Fluid inside the pores remained hot and highly chemically reduced. The surrounding seawater was cold and slightly more chemically oxidized. This imbalance generated a tiny but persistent electrical charge continuously. Researchers search for evidence of the last universal common ancestor. This hypothetical original organism is often referred to as LUCA. Genetic studies suggest LUCA was an extreme deep thermophilic bacterium. It likely thrived in a hot, oxygen-free deep hydrothermal environment. The microbes living at Juan de Fuca share similar traits. Methanogens in the vent fluids produce methane from carbon dioxide. They use hydrogen gas directly as their primary energy source. This specific metabolic pathway is considered one of the most ancient. Scientists sequence the DNA of these modern deep-sea microbes. They look for genetic remnants of the earliest living cells. Exploring these alien environments on Earth presents immense technological challenges. The Juan de Fuca Ridge sits under crushing hydrostatic pressure. At 2,200 meters, pressure exceeds 220 atmospheres. This equals roughly 3,200 pounds per square inch exactly. Every piece of scientific equipment must withstand this immense force. Water penetrates the tiniest flaws in seals or electrical housings. The deep ocean is also completely devoid of natural sunlight. Water absorbs all visible light within the first 1,000 meters. Robotic vehicles must carry their own powerful artificial lighting arrays. High-intensity LED lights illuminate the dark basaltic seafloor for pilots. Temperature extremes add another layer of complexity to vent research. The ambient seawater remains near a frigid 2 degrees Celsius. Black smoker fluids erupt at nearly 400 degrees Celsius. This creates a severe thermal shock environment for any exploring vehicle. Titanium is often used for sensor housings and sampling probes. It resists both the extreme heat and the corrosive fluids. Vent water is highly acidic, with a very low pH. It contains dissolved hydrogen sulfide which corrodes standard marine metals. The submersible Alvin features a specialized titanium personnel sphere inside. This thick metal orb protects 3 occupants from the hostile exterior. Remotely operated vehicles face their own unique deep engineering hurdles. The ROV Jason connects to the surface ship via a tether. This long cable transmits power and high-speed data continuously downward. The tether must be strong enough to resist ocean currents. It must also remain flexible in near-freezing deep water temperatures. Fiber optic strands inside the cable carry high-definition video feeds. Pilots on the surface ship watch the seafloor in real time. Operating a robotic arm at this depth requires immense skill. There is a slight latency in the transmission of commands. The pilot must anticipate movements to avoid damaging fragile chimneys. Long-term monitoring requires even more advanced technological engineering solutions today. The Ocean Observatory's initiative installed a massive cabled network here. Hundreds of kilometers of fiber optic cables cross the seafloor. They connect various sensor nodes directly to a shore station. This eliminates the need for battery replacements and ship deployments. Seismometers detect microscopic tremors in the Juan de Fuca crust. Temperature probes record minute fluctuations in the venting hot fluids. High-definition cameras broadcast live footage of the tube worm colonies. This continuous data stream revolutionizes our understanding of ridge dynamics. Maintaining this underwater network requires constant engineering vigilance and care. The geological processes here create substantial mineral resources over time. Hydrothermal fluids leach metals from the deep oceanic crustal rocks. These metals precipitate when the hot fluids meet cold seawater. They form structures known as seafloor massive sulfide mineral deposits. A single large chimney can weigh thousands of metric tons. The Juan de Fuca Ridge contains numerous extinct vent fields. These older sites no longer emit hot, mineral-rich hydrothermal fluids. Their chimneys have collapsed into large mounds of metallic rubble. Geologists map these deposits using advanced acoustic multibeam sonar techniques. They analyze the exact concentration of valuable industrial heavy metals. Some massive sulfide deposits contain highly sought-after rare earth elements. These elements are crucial for manufacturing modern consumer electronic devices. Neodymium and dysprosium are used in powerful permanent industrial magnets. Tellurium is a vital component in advanced solar panel production. The concentrations in deep-sea deposits often exceed terrestrial mines. This economic reality drives the ongoing debate over seabed mining. Extracting these deep resources presents a monumental oceanographic logistical challenge. Bringing heavy ore to the surface requires massive pumping systems. The environmental cost of such extraction remains largely unknown today. Scientists advocate for extensive baseline studies before any mining begins. Biological resources at the ridge may hold even greater value. Pharmaceutical companies engage in a practice known widely as bioprospecting. They search for novel chemical compounds within deep-sea organisms. Extreme environments force microbes to evolve unique biological defense mechanisms. Some vent bacteria produce powerful natural antibiotic compounds for survival. These could potentially treat drug-resistant bacterial infections in human patients. Other microbes possess enzymes that function at extreme boiling temperatures. Industrial processes often require high heat to manufacture specific chemicals. Standard enzymes break down and denature under these harsh conditions. Deep ocean enzymes provide a robust alternative for industrial manufacturing. Enzymes from hydrothermal vent microbes remain stable at high temperatures. The famous Taq polymerase enzyme was discovered in hot springs. Similar discoveries are now happening at deep ocean vent sites. Researchers isolated a highly heat-resistant enzyme from a vent archaeon. This microbe was named Pyrococcus furiosus, the rushing fireball organism. Its enzymes operate optimally at exactly 100 degrees Celsius. Biotechnology companies utilize these deep-sea enzymes in genetic sequencing. They improve the efficiency of polymerase chain reaction testing methods. The genetic wealth of the Juan de Fuca Ridge is vast. Only a tiny fraction of these microbes have been cultured. The deep ocean environment remains a realm of quiet, immense power. The active hydrothermal vents continue their ancient, steady geological work. They cycle the cold oceans through the crust of the Earth. They nourish delicate life in a dark world without any natural sunlight. The deep waters of the Juan de Fuca Ridge hold global significance. This dark environment directly influences our vast planetary climate system. Hydrothermal vents release enormous amounts of continuous geothermal heat. This localized thermal output gently warms the surrounding abyssal water. Warm deep currents gradually rise toward the ocean surface. This vertical movement helps drive global ocean circulation patterns. Oceanographer Dr. Sylvia Earle has studied these deep thermal dynamics. Her research shows how deep heat alters broad ocean currents. The ridge sits at a depth of roughly 2,000 meters. At this level, water pressure exceeds 200 standard atmospheres. Vent fluids emerge at temperatures reaching 380 degrees. This intense heat transfers directly into the frigid bottom water. The resulting thermal plumes spread outward for hundreds of kilometers. These massive plumes carry essential dissolved minerals across the ocean. Iron and manganese from the vents fertilize distant microscopic plankton. Surface plankton populations absorb significant amounts of atmospheric carbon dioxide. This biological process forms a crucial global carbon sequestration mechanism. The deep ocean ridge acts as a hidden climate regulator. Microbes living near the vents also process dissolved carbon compounds. Chemosynthetic bacteria convert inorganic carbon into stable organic physical matter. This deep biological pump locks carbon in ocean sediments. Scientists measure this carbon flux using advanced acoustic benthic landers. Researchers from the University of Washington monitor these exchanges. Dr. John Delaney pioneered continuous observation of these processes. His team deployed specialized sensors along the axial rift valley. These instruments record dissolved gas concentrations every single passing hour. The data reveals complex interactions between geology and ocean chemistry. Carbon dioxide flows continuously from the Earth mantle into water. Specialized vent microbes rapidly consume this newly released volcanic gas. They prevent excess carbon from reaching the upper ocean layers. This natural filtration system maintains a delicate marine chemical balance. Sulfur compounds also play a vital role in this cycle. Hydrogen sulfide provides the primary energy source for vent bacteria. These microbes oxidize the sulfur to create complex organic molecules. This process completely bypasses the need for any solar energy. The deep ocean sulfur cycle impacts broader global chemical patterns. Nutrients from the ridge eventually upwell along the continental shelf. This upwelling supports rich fisheries along the Pacific Northwest coast. The health of coastal waters depends on these deep vents. Everything in the global ocean remains deeply and fundamentally connected. Future research will further explore these hidden planetary climate connections. Ocean Networks Canada plans extensive new expeditions to the ridge. Upcoming missions will deploy next-generation autonomous underwater vehicles. These robotic explorers can map the seafloor with millimeter precision. Engineers are developing advanced titanium pressure housings for new cameras. New optical sensors will capture unprecedented details of vent life. Scientists want to understand the vast subsurface marine microbial biosphere. Life exists deep within the porous basaltic ocean crust itself. The Integrated Ocean Drilling Program samples these deep rocky layers. Drill ships extract core samples from hundreds of meters below. Researchers analyze these ancient rocks for signs of buried life. Dr. Julie Huber studies these extreme subterranean biological vent communities. Her genetic sequencing reveals entirely unknown branches of microbial life. Environmental DNA sampling allows scientists to identify invisible marine organisms. They filter ocean water to collect microscopic floating genetic material. This technique catalogs biodiversity without disturbing the fragile vent ecosystem. Many fundamental questions about this dark environment remain completely unanswered. We still do not know how vent animals disperse globally. Tiny larvae must travel vast distances between isolated active vents. Ocean currents sweep these fragile organisms across the cold abyss. Biologists are deploying new acoustic tags to track their movements. High-frequency sonar arrays listen for subtle changes in biomass distribution. The Neptune-cabled observatory provides continuous power for these sensors. This fiber-optic network spans over 800 kilometers of seafloor. It connects directly to laboratories on the distant continental mainland. Scientists can adjust deep-sea camera angles from their desks. This real-time connection revolutionizes modern deep marine biological research. Upcoming projects will install more seismometers along the fault lines. Researchers aim to predict underwater volcanic eruptions before they occur. Microearthquakes often precede major shifts in the deep tectonic plates. Continuous monitoring helps map the underlying molten magma chamber dynamics. Thermal probes measure the exact heat flux escaping the seafloor. The total energy output equals thousands of commercial power plants. Yet this massive thermal release happens silently in the dark. Remotely operated vehicles like Jason perform delicate manipulative underwater tasks. Robotic arms carefully collect fragile fluid samples from boiling vents. Titanium syringes capture pristine water before it mixes with seawater. Mass spectrometers analyze these chemical samples aboard the surface ship. Every expedition reveals newly discovered species of deep-sea invertebrates. The Juan de Fuca Ridge remains a critical natural laboratory. Embrace the tranquil mystery of the deep marine natural environment. The scientific journey of discovery will steadily continue tomorrow morning. New robotic explorers will dive into the dark ocean waters. Researchers will uncover more secrets hidden within the rocky crust. But for now, the deep sea simply rests in shadow. The hydrothermal vents provide a steady, comforting planetary geological heartbeat. Their thermal energy pulses softly through the cold bottom waters. This natural rhythm invites a state of deep physical relaxation. Your breathing can match the slow drift of deep currents. Your muscles can release tension into the vast ocean expanse. The mysteries of the deep sea are safe and secure. They wait patiently for the next generation of curious minds. The Endeavour segment will remain a protected underwater biological sanctuary. The axial seamount will continue to host unique microbial life. The Explorer Ridge will slowly build new towering sulfide chimneys. These geological features are permanent fixtures of our blue planet. They remind us of the incredible resilience of natural life. Even in the harshest conditions, beautiful ecosystems manage to thrive. This knowledge brings a sense of comfort and deep peace. The Earth is a wonderfully complex, perfectly balanced living biological system. Every deep sea vent plays a crucial role in it. Every microscopic organism contributes to the global chemical marine balance. We are all connected to this vast underwater volcanic network. The air we breathe is shaped by these deep oceans. The climate we experience is regulated by these abyssal currents. As you prepare for sleep, hold on to this tranquil connection. Let the imagery of the deep sea wash over you. The darkness of the deep ocean is not frightening here. It is a soft, welcoming blanket of pure liquid night. It wraps around the rugged contours of the volcanic ridge. It holds the delicate marine snow suspended in the water. It cradles the sleeping forms of bizarre deep-sea fish. You can share in this profound, undisturbed aquatic deep slumber. The busy surface world fades away into a distant, quiet memory. Only the gentle, soothing warmth of the hydrothermal vents remains now. Only the slow, steady movement of the deep ocean currents. The Juan de Fuca Ridge bids you a peaceful rest. Its ancient volcanic rocks stand as silent guardians of sleep. Its thriving biological communities whisper a soft, rhythmic nighttime lullaby. Thank you for exploring this hidden underwater realm with us. Thank you for watching. Sweet dreams.